Okay, so we have a certain set of data here. And what we have here is a two-factor experiment. So we're looking for the effect of both brand, whether we have the golf ball brand A, B, C, and D, and what club we hit the golf ball with, i.e. a driver or a 5-iron. We also want to see if there's any interaction between the driver and the brand. So we're looking at both the main factor effect, driver or 5-iron, and what type of brand it is. So we're looking at those main factor effects, and we're also looking at the interaction between the factors. So let's kind of draw this out. Oh God, let's get back to black. So we have factor A, and we have two levels of factor A. We have the driver and the 5-iron. Get it right. And then we have the brands A, B, C, and D from the brand factor. So that's got A, B, C, and D. And there we have the brands. Beautiful table here. A, B, C, and D. And you can see all these lines are a nice even length. We have like 4 observations. Let me just write the first one in. There'll be 3 blanks. These are just numbers. So we have 4 observations for each combination of brand and club. Okay, so let's just have a little bit of notation here before we do the math. So let's just do A is the number of levels for factor A. B is the number of levels for factor B. And R is the number of replications in a cell. So i.e. how many times you repeat for each combination of factor and golf club here. Now N, the total number of observations. So here we have like 4 observations in each cell. So it's basically A times B times R. So in this example, it would be 2 times 4 times 4 is 32. Okay. And let's kind of have another. Remember my notation from before. This is the overall mean. And then for each factor A, this is X, the mean for row 1. This is the mean for row 2. Then this is the mean for column 1. Gotta have the line on it. 2, 3, and then 4. So that's just the mean of every x1 dot. This would just be the mean of all of those values here. And let's get a red. X dot 1 would be the mean of all of those values here. The mean of those 8, the mean of those 16. So the total sum of squares is going to be sigma. So this is basically saying I equals for each of my A levels and each of my B levels and each of my replications. Oops, K there. K equals 1 to R. Basically, X I J K minus X double bar squared. And again, this is just notation to say we're cycling through each of my items for every row, every column, every item in the cell. We're subtracting the overall mean and the square. So what we've done a lot of times before in the class, this is just kind of like my sum of squares. Let's get a little bit smaller. You can still see that. Okay, so next we're going to have my sum of squares for factor A. Notice now we don't have a sum of squares for treatments because we have two treatments. So I mean we have two factors in the treatment. So we're basically aggregating across B and R. So for row A, we've got across all our brands B and all the replications. So we multiply by the number of items. And this is for I equals 1 to A. Xi, X bar I dot, minus X double bar squared. So again, this is the difference between the treatment means and the overall means. So this is kind of, you know, between level design. And then you can imagine it's something similar for B. And again, this is just really just saying how different are the B means. By saying how different they are from their overall mean. If they're all very close to the overall mean, this is going to be low. If they're all kind of quite different from each other and from the overall mean, then it's going to be high. But we've not finished. And again, we're not going to prove this all from first principles. It's more kind of a bit of intuition. So sum of squares AB. And again, we're looking at the sum of squares for each of the individual cells. And we're looking A, R, so it's R times I equals 1 to A times J equals 1 to B. And what we're doing is we're doing the mean for each of the cells minus the row mean. So we're just taking off the effect of the factor A and the factor B and kind of seeing what's left. Again, let's move it up a little bit and make it a little bit smaller. You notice the original is getting down to minute size. But this time, plus X double bar. And this is just essentially because it's xi dot minus X double bar. It's just basically been subtracted. It's just been subtracted twice, which is why it's actually positive. So we have the sum of squares for the interaction. Now, let's just think what the degrees of freedom are here. The degrees of freedom are, basically we have ABR items minus, we're calculating one mean, so we track 1 degree of freedom for the overall mean. So it's ABR minus 1. But what's ABR? As we defined, so it's just n minus 1. Degrees of freedom for A is we have an observation. So I've got a fly running over my screen. Get away, fly. We have, so that just completely ruined my train of thought. So for the sum of squares for A, we've got these A values, these A means, and we subtract the overall mean, so we lose the degree of freedom, A minus 1. Same here, we have B minus 1. And here, let me just move up. Degrees of freedom. Now, let me just write it out and then I'll try and explain a little bit. A minus 1 times B minus 1. Okay. Sorry. Which is AB. So that's the number of observations here. Then we take away minus A minus B for each of these number of means here. But we add kind of a mean back. So AB plus 1. Okay, so let's kind of put this into the ANOVA table. And first, let's just do kind of what we did before. So we have our total sum of squares equals the sum of squares for A. And again, proving this from scratch is a little bit beyond this course. But feel free if you've got, like, I know you PhD students have got a lot of spare time. If you want to play around with these and try and prove it yourself, then you're very, very welcome. I might give you a gold star. So we have SSAB, and then finally we still have some error, so we have the sum of squared error. And we could actually put this into an ANOVA table. So let's just do source, degrees of freedom, sum of squares, mean squared, and then the F. So we've got the sources, we've got factor A, factor B, the interaction AB. We're going to have the error. And then we have the total. And so let's just fill in our degrees of freedom. This was A minus 1, B minus 1, A minus 1 times B minus 1, and then N minus 1, or ABR minus 1. And you could just kind of, the other one is going to be ABR minus 1. Okay, let's just to show the error term. If we have, remember, the ANOVA table, everything adds up to the total. So the total is N minus 1, which is in fact, remember it was ABR minus 1. So error, degrees of freedom. So ABR minus 1 minus A minus 1 minus B minus 1 minus A minus 1 times B minus 1, which is equal to, let me just move up a little bit, minus A plus 1, two minuses, minus B plus 1, minus AB. Now we have minus A and minus B, but there's a minus here, so those are both pluses. So plus A plus B. Minus 1 times minus 1 is 1, times minus is a minus 1. So let's get the red pen out. So we have minus A, minus B, plus B, plus 1, minus 1, plus 1, minus 1, which gives us ABR minus AB, which is equal to AB R minus 1. So the degrees of freedom adding up hold. Okay, so maybe that was a little bit over the top. I'm not going to ask you to prove that in an exam, but just to show you I wasn't bringing those numbers out of anywhere. So now we have the sum of squares for A, the sum of squares for B, the sum of squares for AB, and the sum of squares error, given the total sum of squares, so the sum of squares add up to the total sum of squares. Now you can guess where we're going here. We have mean squared A equals sum of squared A all over A minus 1. Mean squared B equals sum of squared B all over B minus 1. Mean squared AB equals sum of squared AB all over A minus 1 times B minus 1. Sorry, I didn't give myself enough room here. And we have mean squared error. I'll just put out the table. Mean squared error is equal to sum of squared error all over AB R minus 1. And then the FA is the mean squared A all over the mean squared error. FB is mean squared B all over mean squared error. FAB is mean squared AB all over mean squared error. So we essentially have 3 F-tests there. Each have the denominator degrees of freedom ABR minus 1, and the 3 tests have numerator degrees of freedom A minus 1, B minus 1, A minus 1 times B minus 1. Now I'm not going to write all those tests out, so I just want to show you a few quick things. The first is essentially what we're going to be doing with the sum of squares. So here it's the total sum of squares. Now with the completely randomized design, let me just take a full screen snip. With the completely randomized design, we were splitting this up into the sum of squared treatment and the sum of squared error. Now here, the degrees of freedom actually pretty much remain the same. This is n minus AB, which is in fact ABR minus AB equals ABR minus 1, just to show you that it was the same as we had before. So the errors don't change, but now we're splitting the total sum of squares into sum of squares A, sum of squares B, and sum of squares AB. Now that's kind of interesting here that we, with the blocking factor, we actually split the error. Here we're actually splitting the treatments into 2. And this leads us to what we're going to do. Is we're going to test the overall, basically we're going to treat it as a completely randomized design. And test for all the means if at least one is not equal to 0. And then if we get a significant result, we test the individual factors. We test the means for factor A, for factor B, and for the interaction. So let's just have a quick look at these F-tests. So let me remove that, and let me do the same for this. So here we have, there are tests for treatment names. So there's no difference among the A-B treatment means. So in this kind of, in our example, there would actually be, 8, golf club, 8 club times brand means. So we're testing, basically we're treating it as a completely randomized design with 8 means. And at least 2 treatment means differ. And here we're just treating it like a completely randomized design with 8 levels for the factor. If this is significant, then we do the individual tests. We do the test for the interaction, where the null hypothesis is factors A and B do not interact, and factors A and B do interact. And here we're looking at the mean squared AB. And again, we have this degree of freedom, A times 1 minus B minus 1. And then we have the error degrees of freedom here. We can check for the main effect for factor A. No difference between the A mean levels of factor A. So here this would be the mean for basically the driver equals the mean for the 5-ion. And at least 2-factor A mean levels differ. Mean squared A over mean squared error. And again, we worked it out in the ANOVA table, A minus 1 numerator and the same denominator. The denominator is not changing. Overall test, then split up and do the interaction for A. And let's just have a quick look. And the next slide. Yeah, we couldn't quite fit B on, so we won't have a separate slide. And here we go. Again, so this was factor B. In this case, will be our golf brands. This would be mu A equals mu B equals mu C equals mu D. And at least 2-factor level means differ. And again, B minus 1 numerator, N minus AB equals a denominator. Now, sometimes people will say that you should check the interaction, and if there is an interaction, you don't worry about factor A and B. But I kind of disagree with that. SPSS will calculate all three together, and generally most papers I see reported, we look at the three together. We look if there's something for factor A, a little bit like the diagrams I showed you at the beginning. We look if there's something for factor A, something for factor B, something for the interaction, and those three pieces of information together will kind of give you an overall picture of the results from the experiment. And we do the overall test first. It's almost a little bit like when we did the protected t-tests by saying, okay, we only look at the individual comparisons after we've done the omnibus test. Here it's like an extra level. We only do the individual kind of A, B, and interaction tests if we've done the overall test. So the next video, I'm going to show you the data in SPSS, and I'm going to go through all the tests for our specific example.